Hi, my name's Bob Greenyer, and I'm a volunteer with the Martin Fleischmann Memorial Project. So the date is wrong on that slide there. It is not, in fact, the 31st of August 2023. It is, in fact, the 13th of February 2024. You have not gone back in time. Let me just fix that. Can you hear me whilst I fix that? Oh dear. Can you hear me? Loud and clear. Excellent. So, it's great to have you here with me today. A reasonable quorum, given the fact that it is a Tuesday. I did want to get this out on Sunday, but it wasn't ready. I'm not sure it's ready now, but I want to get it out today in support of Bin-Juine Huang's paper. So should we try that again? Hi, my name's Bob Greenyer, and I'm a volunteer with the Martin Fleischmann Memorial Project. So welcome this 13th of February 2024 to this method for obtaining energy. Anatoly Fedorovich Kladov. Hi, Chris Marston, Josh S. Hi, Ret Oracle Vanilla Isis. Very good name. D2105K. Sebastian Sosnowski. Simeon Hain. I'll get your name right eventually. Venom K. Ken Pratt. And we have Gordon Doherty in the house. Thank you for joining us. And hello, Mark Alexander, Tony Yaboni. Corky Goss. Mr. Gate Mode. It's great to see some new regulars joining us on our journey. And sorry to those people that are unable to join us because it's not a Sunday on the weekend. Hi, Thomas Kuntz. From Switzerland, and Neanderthal and John Weir. Okay. So, I first mentioned Anatoly Fedorovich Kladov in my 28th of September 2022 presentation to the Condensed Matter Nuclear Science group in Assisi in Italy. And this was the cover slide for that. Ultra, a simple, quick and repeatable demonstration of the Lena process. And in it, I quoted some of this reference up here, roslo.narod.ru/tep/index.htm. And it's actually one of the references in the Bin-Juine Huang paper. I actually couldn't find the patent. However, it claimed that the patent was observing 2 to 7 times COP, that is more energy out than electrical energy consumed. That's more thermal energy out than consumed. And there were, for instance, the synthesis of iron, claimed by the fusion of H2O, producing this. And potentially I considered that that might be a weak interaction. Now, why this is very interesting to me is I didn't know when I knew of this patent that it was anything more than just an energy patent, i.e. a cavitator that is producing over unity. When we look at this patent, which took some considerable effort to assemble, and I must thank greatly Alexander Shishkin. Why? Because in the Russian analysis of Bin-Juine Huang et al.'s paper, after Alexander Parkhomov had finished his assessment, and I'm glad to say that Alexander Parkhomov told me yesterday he is now out of prison. Prison? Not prison. He's never been in prison. Out of hospital. Oh dear, it's not going well tonight. Out of hospital. Sadly, he had a micro stroke, and they say he's good now and he's in recovery. So I hope you will join with me in wishing him well. He's 79 just on the last day in January, so February rather. January, I think January. He's doing well at the moment, and I hope for his speedy recovery. After he gave his assessment, and I will get that published, I need to translate some slides. Alexander Shishkin spoke about his cavitator, and if you remember, his cavitator was the one that he was using to try and mix oil and water for a customer, and then he saw this, he felt ill near it, and then he felt there might be some sort of emissions, and he then put X-ray film around it and found that there were these birdies, and that started a 9-year journey for him exploring these magnetic monopole strange radiation emissions from cavitating water in his case. And what he disclosed, as far as I'm aware, for the first time in response to the Bin-Juine Huang paper, is that they analyzed the water coming out of that cavitator, and they actually found the synthesis of increased levels of deuterium, oxide, heavy water, in that sense, and also, and they only looked for oxygen 18, they found an increase in oxygen 18. So in both cases, one might assume that there are being neutrons produced, and they are respectively increasing the mass of protium to deuterium, and respectively the mass of oxygen 16 through oxygen 17 to oxygen 18. Of course, our interest in the Bin-Juine Huang paper was the initial production of oxygen 17. And one might imagine that the neutron that is being produced is unlikely to be a neutron stripping reaction. It's more likely to be a neutron synthesis reaction. And the question is, how exactly does that happen? He only had a few slides, and at the end of it, he referred to two people who he thought were absolute giants in the field of cavitation research, and one of those was Kladov. So I took the opportunity of reaching out to him afterwards and said, look, have you got access to his patent? Because I see it quoted, but I can't seem to find it. And so he sent me a link, which I will share in the blog tomorrow, associated with this live stream, of the link that he sent me. Now, that link shows a Russian patent awarded on a Russian server, and you can even find a rough translation of that via Google Patents. But what I will say is the Russian version of that patent, as typed on the Russian server, and the translation is you basically can't work out some salient facts, because whoever transcribed that, and this is sometimes the case, you actually get a patent clerk or a typist who kind of misses the importance of an equal sign, or misses them, or there's some sort of OCR system that's involved and it kind of misinterprets something. And so I went on the search for other versions of this, and also for the tables that were in there. And having had the correct code for the patent and Kladov's full name, I was able to find a version that was awarded on the EPA, the European patent site, and it was also had its abstract in English and in French. Some of the errors were carried across, but interestingly, it had the original hand-typed and part handwritten Russian patent rather than the one that was available on the Russian server. This additionally had some problems. It was also, and as you will see, it's very low quality in terms of it's a bitmap scan at a low resolution. I don't even know whether it's 150 dpi of the Russian text. And so, but combining all of these sources, I think I've been able to come up with a pretty good translation. I'm not quite done with it, but I felt I wanted to get this out to you today because of its importance. And I feel possibly, potentially, this patent, which is expired by some 10 years nearly, it's pretty much 30 years old since this was applied for. It provides some incredible opportunities. One, it verifies very neatly and precisely the claimed observations of Bin-Juine Huang in terms of production of a certain level of excess within a ballpark range without the emission of radiation. It also shows conclusively, in my view, that they had nuclear processes going on, but not in an ordinary water system where it is flowing through rather than being recycled. So that is very, very interesting. It also shows how additives can be added where the additives promote the production of certain types of nuclear signature-based radiation. Now, we have to put Kladov's time and his resources in context. I've told you before about a exhibition I believe I went to, I think in 1993 at the National Exhibition Centre, when in the UK, where there were vast numbers of formerly Soviet scientists that had come over to try and sell their technology, having had the rug pulled from under them in the collapse of the Soviet Union. And I was absolutely blown away by this incredible plethora of technology. And these people were like ready to give it away for almost nothing. This falls into that category because, as you'll see, I show here, the hate generator was from the 1980s. But the patent that I will show you refers to a previous patent that was patented, I think, in 1992. And that is in English on the European patent server for the actual cavitation device itself. So what you could imagine was happening at this time is people were desperately trying as fast as they could to get their research, which was now no one cared about, no one was going to hassle them. It hadn't been made public. It was all formally secret, and they were trying to patent these technologies and get them out and see if they could fund, you know, their ongoing research or practical embodiments. And I imagine that these two patents from Kladov fell into this category. I mean, I don't know, but if the work was being conducted, as one might imagine, in the 1980s in Soviet Russia, they didn't have the kind of mass spectrometer that was available to Bin-Juine Huang, the one that is provided by Maztec, the one of the suppliers to and analyzers in the Taiwan semiconductor industry. These are some of the best pieces of kit, and they just weren't available. So the idea of doing gas mass spectrometry wasn't really an option on a big industrial unit like the one that we will look at. Secondly, having seen SEM images taken in the 1980s by George Hathaway and by the Max Planck Institute and others, well-resourced people from the 1980s of John Hutchison's material, I can say that the resolution and the ease of use of those are very limited, and the ability to analyze using EDS the X-rays that come back from the impinging beam of high-energy electrons is also limited and difficult to use. What was very widely available in Soviet Russia and the Soviet countries was radiation detectors in the form of some of the best ever made neutron detectors, 3 helium and boron-10, and also gamma and beta detectors in the form of the beautiful pancake detectors that were made in Russia and other types of Geiger-Müller devices. So what they had in abundance were these type of photon, beta particle, and neutron particle measuring devices. And many of the ones that even we have used have been old stock, new old stock from Soviet Russia. Large amount of them made in Ukraine, in fact. And so it is not surprising that what he chose to do was try and demonstrate the production of nuclear products using this method and nuclear transmutation by seeing this proxy signal. What I was surprised to find that is that he actually did this as part of this patent. I thought the patent was just, we're showing we're producing excess heat and this is how you do it. No, it's a very thorough patent. And as I said to you before, there are specific chemical compounds it suggests to use to see certain types of emissions. And this is something that can be explored by Bin-Juine Huang and other researchers. The patent for the actual cavitator is also expired, and we are talking about tens and hundreds of kilowatts. So in the case of Bin-Juine Huang, he's typically using 6 to 10 kilowatts of input energy, electrical, to preheat the water such that it is in a multi-phase state as it goes through the injector. If it's not in that multi-phase state, it will not produce excess heat. Now, defining what is the optimum pressure variations to produce the excess heat, which is then accumulated in a thermal accumulator, that is something that has been something of interest to nail down for Bin-Juine Huang. And in fact, it would appear that that is the single basic claim of Kladov's 1993 paper. That is to say, he has defined the pressure change domain over which you create the right size cavitation bubbles that have the right energy to do nuclear processes. And you'll see that in the course of this work, this patent, he realized that by running water in a loop rather than just running it once through the device or running it through maybe a heat exchanger, he was able to show an increase in the emissions that are coming from it, which implies that there was a stepwise process of synthesis of nucleons. And that explains to me why he went on from his heat generating cavitator research and made these claims in his further research between 1997 and 2002. And this is in the same article up here. It shows cavitation destruction of matter. The purpose of this work is to demonstrate the real possibility of cavitation destruction of matter on the example of transmutation of various chemical elements, showing at least 3 main modes of destruction. Changing the structure of a nuclei by adding 1 or more structural elements. So, in my view, this would be adding a proton and an electron and an antineutrino to oxygen-16 synthesizing oxygen-17. The more structural elements would be compliant with that statement, and this would lead to oxygen-17, then fusing oxygen-17 together to make sulfur-34, and then changing the structure of the nuclide by dividing it into several fragments. So if we take sulfur-34 and we divide that and we get carbon 12 and we get neon 22, that would be in line with his second statement there. And then the last one there is changing the structure of the nuclide by dividing it into the smallest structural fragments or by the complete transformation of matter into radiation. That is to say, into field forms of the existence of matter. So this is baryon decay. As we have discussed, was claimed to be possible by the fractal toroidal moment that they call hypertors or supertors in the mainstream physics area and in the Russian field. And he clarifies down here, the basic processes of cavitation destruction of matter occur in the ultrasonic activator almost simultaneously. So all of these things are going on. Now, if you remember Leclerc, he was able to, by running this device a fair amount of time, he was able to synthesize, it was claimed, a vast number of nuclei. And so this kind of statement that is being made by Kladov supports that. And he's saying that basically all of these things occur simultaneously and essentially, as far as I can see, almost immediately. And of course, during this period as well, he observed large reductions in added cesium-137. So for a third 20-hour treatment period, 24 mil of radioactive cesium-137 and 10 milligrams of stable cesium chloride were added to the solution. The decrease in the radioactivity of the solution was 65.1%. So that's kind of like pretty impressive. That's almost 2 half-lives. So in a 20-hour period. Okay. So he, in this same research, showed that the cavitation destruction of matter, if you had 2 hours of processing, and you could imagine that this water is cycling through the process, you ended up with a synthesis of 19 elements, and 8 hours, 23 elements, 24 hours, 29 elements, and 360 hours of processing, 55 elements. And he suggests that there may be supermicroscopic black holes, and that you may be able to use a super shortwave electromagnetic detector to detect them. Okay. So if you are synthesizing a vast number of elements, then in a long period of time, I think it is reasonable to expect that Bin's work is valid. Now, what I'm going to do is I'm going to go into the patent and its justification. I'm going to show you the Russian one and some of the errors on there, which were complicating and confounding. And then I'll show you the rough and ready original document that it all came from. Okay, so this is the original Russian patent here. RU2054-604C1, and I will give all of the links in the blog. And you can see here actually on the second page, it's actually got some English here. Now, when you are looking at this, it has these equations here which are just a complete mess. They don't make any sense, and I've kind of worked out what they are, and I've worked out how what they mean. So, for instance, here, P1, this means from 03 to 07, brackets P2, P3. I mean, this just doesn't make any sense. And this one, P2 plus P3 dot P1 to 1. I mean, or from 1 to 10 sigma. It just doesn't make sense. And there is a lot of this going on in this patent here. So as we go down, there's more of this nonsense down here. I mean, what does this mean? What does this mean? It's just total gobbledygook. And this is the awarded patent on the Russian server. So you can imagine that it's like someone knew this works. It's been demonstrated, and this is what the guy is saying is it is. But you know, it's a little bit confusing. But the person reviewing it knows that the device works. So let's just give it the patent. Now you could argue that this makes it difficult, but it's been 30 years. 30 years since this was submitted, all bar a few months, and I really wonder if anyone's bothered to look at it. It might have been the case that so many patents were applied for. It was just a flood of extraordinary patents were applied for. And this one slipped under the radar. Maybe. Maybe not. Not anymore. Okay, so the actual patent, which I only found available from the European patent servers, and hopefully this works sometimes. Sorry for the strobing there. Let's see if I can fix that. It has some issues sometimes. Dear, it's having issues. Okay, let's hope this works now. Right, so this is the original document, and you can see it's basically patented everywhere. It is an awarded patent. And you can see here that it's very low res scanned document, but it actually has something that makes a little bit more sense. So if we go up to this one, which is now not working. Oh dear. Give me a break. See. Okay. You can see P1 open bracket 0.3 minus, it's just nonsense. Whereas here it says very clearly P1 equals from 0.3 to 0.7 and bracket again, I can't even read it now. I have worked it out. P2 plus P3 minus P1 equals from 1 to 10 sigma. It just makes a hell of a lot more sense. And this goes through the patent where you can actually kind of work out stuff that isn't in the other records of this patent. So again, here, this makes sense. If we go down to the other bit we were looking at earlier, this makes a lot more sense. Okay? So by working through these, I've been able to come up with something which we can look at. Hi, DIY Projects with Chances. Hi, Sitful Heshwaj. Hi, Lithnik. Great to have you here. And Graham Cracker. So, let's go and have a look at this. I think this is probably one of the most useful things I have done in many years. Let's have a look at it now. So I would have liked to have had lots of slides prepared, and I would have done that, but I haven't. So you're going to get what you're going to get. So here it is. This will be published probably tomorrow. Method for obtaining energy, Anatoly Fedorovich Kladov. Okay. And I will do a read through of the patent for those that want to listen in that way. So the field is power engineering. And the effect is increased in efficiency. And that is 9 figures, 1 table. Abstract. The proposed method of obtaining energy involves feeding a liquid phase substance into a treatment zone where cavitation bubbles are created in the substance by producing a fluctuating pressure with constant and variable components based on the following relationships. P1 equals from 0.3 to 0.7, and P2 plus P3. So that is from 0.3 to 0.7 times P2 plus 3, and P2 plus P3 minus P1 equals from 1 to 10 sigma. Okay? This will make sense later. It took a long time for me to rebuild these equations and to actually verify what I had rebuilt, and it all makes sense. So the hard work has been done. This is a real opportunity for producing real heat generation devices using this and his previous patent. In which P1 represents the constant pressure component in megapascals, P2 represents the variable pressure component in megapascals, P3 represents the saturated vapor pressure in megapascals of the substance being treated at the temperature at which it is fed into the treatment zone, and sigma is the tensile strength of the substance being treated at the temperature at which it is fed into the treatment zone. Description. The invention relates to energy, in particular to the energy of strong interactions of elementary particles. What he is saying there is he is implying that this allows us to yield full-on nuclear level interaction energies. Currently, there are many methods for producing energy that are widely known. For example, the method of generating thermal energy from solar radiation, kinetic energy from wind, water, thermal energy released during the burning of fossil fuels, coal, oil and gas, thermal energy released during the fission of heavy nuclei of chemical elements, the energy released during the fusion of the light nuclei of chemical elements, and the energy released during the fusion of matter and antimatter. However, the radiation intensity of solar energy in the optical range is only a few volts per square meter of surface. Therefore, a huge area is required to obtain the energy of solar radiation on an industrial scale. Wind energy is also characterized by low intensity, despite the fact that it is 2 to 3 orders of magnitude higher than the intensity of solar radiation. The concentration of energy from water movement by 2 to 3 orders of magnitude exceeds the concentration of wind energy. This value, which is approximately 1 megavolt per square meter, is acceptable for the industrial production of energy from moving masses of water, which is confirmed by the development of hydropower. Negative factors in this case are the need to create reservoirs and flooding of large areas of the Earth's surface, high capital costs for the construction of hydropower facilities, and limited resources. The energy released during the burning of fossil fuels, coal, oil and gas, is currently the main type of energy used on an industrial scale. Negative factors are environmental pollution during the extraction and transportation of fuel combustion products and heat, while the efficiency of thermal stations does not exceed 40% for mines, open pits, ash dumps, heaps, heat plants, cooling ponds, power lines, and other structures included in the fuel energy complex. Huge areas are allocated, which is a consequence of insufficient concentration of energy. A widely known method of generating energy is at thermal power plants. This method consists of burning organic fuel in the furnace of a steam boiler, where the chemical energy of the fuel is converted into the thermal energy of water vapor. However, for the implementation of this method, it requires a large consumption for the extraction of fossil fuels for its transportation and combustion In addition, fuel combustion leads to environmental pollution. At the same time, a large amount of substance at the stage of combustion is released into the atmosphere and hydrosphere in the form of gaseous products of combustion. Of all the chemical energy contained in fossil fuels, only about 30% reaches the consumer in the form of electrical energy. The rest is scattered in the environment, which reduces the efficiency of thermal power plants and upsets the ecological balance of the environment. So these are your standard platitudes, these standard comments that you might expect, but it's well stated, I think, and also showing the orders of magnitude between different types of energy is an important consideration. A widely known method of generating energy at nuclear power plants is that water is supplied to the active zone of a nuclear reactor where it is heated using nuclear fuel. Heated water is removed from the treatment area for subsequent use as intended. However, the cost of extracting and preparing nuclear fuel for a nuclear reactor are high, which negatively affects the cost of energy received. In addition, nuclear fuel cannot be fully used in a nuclear reactor, which significantly reduces the efficiency of the latter. Moreover, the fuel of nuclear power plants is used at about 30 times less efficiently than that used in thermal power plants. Potentially, the development of nuclear energy poses serious problems related to environmental protection. Accidents that occurred at a number of nuclear power plants convincingly testify to this. Of course, this was before Fukushima, and we don't want another one. However, this next paragraph reveals something that I was not aware of. I don't know if anyone else is aware of in the low-energy nuclear reactions community, but we will investigate it. A known method of obtaining energy, which, according to its essential features, is the closest to the invention, is US patent number US 4333796A, 19th of May, 1978. This method involves supplying liquid lithium to the treatment zone, where it is subjected to periodic acoustic forces to create cavitation bubbles in it, resulting in a fusion reaction. Really? I didn't know that. Let's have a look at that. Here we go. This is from one Hugh G. Flynn, and it was assigned to an individual, and it was granted on the in 1982. It was granted in 1982, 40 and a half years ago, and it expired 20 years later in 2002. And what is this? Well, essentially, there's two different reactors that are disclosed in this patent. Each comprises of a chamber containing a liquid host metal such as lithium or an alloy thereof. Acoustical horns in the chamber walls operate to vary the ambient pressure in the liquid metal, creating therein small bubbles which are caused to grow to maximum sizes and then collapse violently in two steps. In the first stage, the bubble contents remain at the temperature of the host liquid. But in the second stage, the increasing speed of collapse causes an adiabatic compression of the bubble contents and of the thin shell of liquid surrounding the bubble. Application of a positive pressure on the bubble accelerates this adiabatic stage and causes the bubble to contract to smaller radius, thus increasing maximum temperatures and pressures reached within the bubble. At or near its minimum radius, the bubble generates a very intense shock wave, creating high pressures and temperatures in the host liquid. These extremely high pressures and temperatures can occur both within the bubbles and in the host liquid and cause hydrogen isotopes in the bubbles and liquid to undergo thermonuclear reactions. In one type of CFR, the thermonuclear reaction is generated by cavitation bubbles within the liquid metal itself, and in the other type of reaction takes place primarily within the bubbles. The fusion reactions generate energy that is absorbed as heat by the liquid metal, and this heat is removed from the liquid by conduction through the acoustical horns to external heat exchanger without any pumping of the liquid metal. Okay. The drawings are quite neat and pretty self-explanatory. So here is one of the devices here. You have your liquid metal. These are the same kind of horns that are being used by the Italian researchers in their mercury experiments, where they do sound into mercury. Only this work is a couple of decades before. And so you can see the focusing of the sound. And then if we go to the second drawing, if it's there, here. In the second drawing, you can see they have the cavitator here. They have some water cooling on the outside here to extract the heat from the horns. And they have a secondary lithium blanket or something here maybe. And neutrons that are produced in here come out here and produce tritium. And the tritium can go round. So you feed it deuterium. Fusion occurs. Some of the fusion products are neutrons. And the neutrons come through into the secondary chamber, splitting tritium, and that goes in. So you end up with a tritium-deuterium fusion reaction when you only need to start with deuterium. So that really is that. It's really rather neat little patent. And they suggest these type of elements. They have indium, tin, aluminium, beryllium, and lithium. So it says here, for this invention, the host liquid must be one with a speed of sound as large as possible, and thus the host liquid must be a liquid metal. While all liquid metals have large speeds of sound, lithium and beryllium have the largest speeds of sound over a wide range of pressures. One important characteristic of a liquid metal is its vapor pressure. Listed below are the vapor pressures of several liquid metals at their melting points. So there we go, and that's what we have. And so you can go and have a look at this patent in your own time. It walks through these expansions and the vapor pressure, and so there's some similar aspects to this patent. But of course, you need lithium, you need deuterium, you need to be able to handle large fluxes potentially of synthesis of tritium. So here, type 2 CFR. The type 2 CFR maximizes the production of tritium and other useful products through thermonuclear fusion inside collapsing bubbles. The bubble contains hydrogen isotopes and vapor of the host metal, and in one mode of operation, lithium vapor as well. In a type 2 CFR, fusion is brought about by the high temperatures and pressures caused by adiabatic compression of the bubble's contents in the thermal phase of collapse. The host liquid is tin, although any one of the several gamma-type metals such as indium, thallium, or gallium may be used. Characteristics of tin that make its selection useful are its low vapor pressure over a wide range of operating temperatures, the very low or zero solubility of hydrogen isotopes of hydrogen in the liquid, and the instability of its hydrides in the range of operating temperatures. So, yes, like the Cardone group, they are suggesting the use of various metals in liquid state. Of course, Cardone only used mercury. So I think that this could be considered a much more early version of liquid metal used with sound to initiate fusion processes. So that is what Kladov is saying here is the most similar patent to the one that is being discussed here. Right. The basis of the invention is the task of creating a method of producing energy that would eliminate the cost of production, preparation, and transportation of fuel. That is gold. That is absolutely solid genius there. You just need water and the device itself, some electricity, which could be provided to drive the drive shaft from any other means, i.e. Grid supply, or by solar, or by wind or whatever, or it could be mechanically supplied by wind, or it could be anyway. So you have the cavitation going on that needs to be supplied. You still need some electricity for the preheating of the fluid. Okay, but one could argue it preheats itself with the cavitation. So honestly, you know, there are ways where you can really gain energy in this, in very interesting energy trains. Okay, so the basis of the invention is the task of creating a method of producing energy that would eliminate the cost of production, preparation, and transportation of fuel, and would also allow to use any substance in a liquid state or its working or as a working medium. Right. So this is a generalized version of a patent that would produce energy from a fluid working medium. This problem is solved by creating a method of generating energy, including feeding the substance in the liquid phase to the treatment zone and creating cavitation bubbles in the substance. While according to the invention, cavitation bubbles in the substance are created by creating a periodically changing pressure having constant and variable components, and these components are selected from the following ratios. P1 is from 0.3 to 0.7 times P2 plus P3, and P2 plus P3 minus P1 equals from 1 to 10 sigma, where P1 is the constant pressure component in megapascals, P2 is the variable pressure component in megapascals, and P3 is the pressure of the saturated vapor of the processed substance at a temperature of its supply to the treatment zone. Sigma is tensile strength of the processed substance at the temperature of its supply to the treatment zone. Right. This is something which I want to reiterate again. When I visited the lab at University of Missouri at ICCF 18, I think in 2013, I saw them doing a so-called Charlani replication where they had wound the thing on a ceramic support and had it in a calorimeter where everything was exactly the same temperature. The same mistake was made when they tried to replicate GS 5.2. They put it all in a brick cave, making sure everything was exactly the same temperature. I saw the same error being made with the $10 million that was frankly completely wasted by Google by making this very fancy calorimeter and having things at exactly the same temperature. Over and over and over again, this error is made. In the case of Alexander Parkhomov, he had his reactors in free air. This allows for thermal gradients. In the case of Chelani's original wire system that we replicated, he had mica supports, and we observed and shared a video where we observed that the wire was 100-degree difference between the area that it was connected to the supports and where it was in free hydrogen. When we were with Piantelli, and I reported this in the Q&A session in 2019 at ICCF 22, when I was presenting Alexander Parkhomov's 225-day reactor, which, by the way, produced more than 60 times the yield of energy than the tokamak that is being celebrated recently in the UK. What I shared there was what Piantelli said, that in his patent, in his standard Piantelli-Ficcardi reactor, he had a solenoid wound down in the diagram as a schematic of where the solenoid would be. But what he shared with us is that the solenoid, and what I shared in 2019, is that the solenoid was condensed up one end, and then like you've got a spring, and you're stretching it out, and it kind of like logarithmically stretches out, okay? What this did meant that over, let's say, his 10 centimeter nickel rod, it meant that there was a thermal gradient. And when the area of the nickel rod got to the absolute perfect temperature to initiate the reaction, it produced heat. And what that did was it caused the area around that and itself to raise in temperature. It means it went out of the correct thermal temperature, terahertz radiation, for it to operate. But because it was a gradient, it could move along the rod. And when it got too far up, then it couldn't sustain, it would move down. And so when he showed, I held this thing in my hand, the operating range in his reactor was a 6mm roughly segment of that nickel rod. Now, if you are trying to get everything to exactly the same temperature, you have a scenario where your Chelani wire or your nickel or your nickel powder in your Google attempted failure, total failure of replication of Parkhomov's work, you have it such that it's all at the same temperature. So as soon as it gets to the temperature at which the process might work, it then ceases to work. So you're guaranteeing failure by building a reactor like this. What happens in this work by Kladov and by the work of Bin-Juine Huang is that the cavitation system has a control of the temperature input, water, and of the pressure differences, and the accumulated generated heat goes elsewhere. And then you either use fresh water at that suitable temperature range, or you cool and extract further energy out of the heated water by cavitation, and then you feed it in at the controlled input temperature. The same thing is being done by Kladov. And the reason is because in the system, in many LENR systems, if you do not get the right thermal temperature, you change so many parameters with just changing the thermal temperature. You change the conductivity of ionic ceramics. You change the conductivity of heating elements. You change the tensile strength of reactor components. You change the vapor pressure. You change the tearing of a meniscus, let's say, or the strength of a so many parameters are changed when you change the temperature. And what is the focus of this work by Kladov is recognizing that you have to have things within a specific range to generate the power, and then you go and use that power elsewhere. Okay. Subject to the indicated conditions of simultaneous action and alternating and static pressures on a substance in a liquid phase, cavitation bubbles form in a liquid at the moment when the sum of two quantities, the amplitudes of the alternating pressure and the pressure of saturated vapor of a substance at a given temperature, exceeds the sum of two values, static pressure and fluid strength tearing at a given temperature. There we go. At a given temperature. You need to get the temperature right for everything else to work. You can't just go, "Way, I made something hot," and then it suddenly stops working. You go, "Why did it stop working?" It's, well, the parameters in which it works, you've just changed them, right? This moment in time coincides with the moment of action of the negative half wave of variable pressure. During the action of a positive half wave of alternating pressure on the liquid, the sum of two pressures acts on the cavitation bubbles, the amplitude of the alternating pressure and the static pressure, which tends to compress the bubbles, that is to say, it slams them. It goes, right? At the moment of collapse of the bubbles, their walls, under the action of the pressure difference acting on the cavitation bubbles, accelerate, acquire kinetic energy, and collide in the center. The magnitude of the kinetic energy acquired is sufficient to break the bonds between nucleons. Of course, my view is a little bit beyond that. We are getting the reentrant jets, or we're getting two rarefraction pulses colliding, producing solitons, and the solitons are these vortices, and because you've got charged particles in there, you're going to get a magnetohydrodynamic structure forming. But you know, there wasn't the ability to see these things back then when Kladov was doing it. So this description, I believe, suffices as a simple analog. Okay, so The magnitude of the kinetic energy acquired is sufficient to break the bonds between the nucleons, overcome the repulsive forces of the nuclei, and initiate interaction between the elementary particles contained in the nuclei of the process substance, neutrons, protons, etc. As a result, in the local area of matter, at the moment of the disappearance of the cavitation bubble, its collapse, nuclear reactions occur with the release of a large amount of energy. The energy released in the treatment area is converted into heat in a liquid. This heat is continuously removed from the treatment zone in the form of heated liquid and used as necessary. This heat is continuously removed from the treatment zone in the form of heated liquid and used as necessary, and the cooled liquid is returned to the treatment zone. There you go. That is what I'm saying you need to do. If you do not do this, then the parameters that are based on thermal processes and variabilities will prevent the device from working. And you will see this because he actually characterized it in this patent. If necessary, changes in energy release change the alternating pressure and or static pressure within the specified limits. In this case, the indicated ratio of variable and static pressures must be observed, i.e. you've got to have a feedback system. Now, this was harder and more complicated back then, but there are literally Arduinos which are more than capable of managing what is needed to be managed to control these parameters in this day and age. Since if it is violated, if the variable pressure increases above the specified pressure or the static pressure decreases below the specified pressure, large cavitation bubbles form in the liquid which do not have time to slam, resulting in the termination of energy release. And this is what Bin-Juine Huang has said. We need to try and work out what are the parameters that actually define whether it's doing the cavitation release of energy and not. Well, Ben, here it is. It was already done in the 1980s by Kladov. In the case of an increase in the static pressure above the indicated one or a decrease in the alternating pressure below the indicated one, the cavitation bubbles cannot form in the liquid and therefore the energy release process does not occur. Since in this case the tensile stresses in the liquid being treated are less than the tensile strength of the liquid. It is done. It is done. The proposed method of generating energy can be carried out in a known ultrasonic activator application PCT RU92000195. And this is here. And it is on the European Application Patent Server here. And very conveniently, you can see it and go through it. That is the cover slide. It is actually all in English, and despite this is an earlier patent, this is filed on the 2nd of November 1992. So yes, this is over 30 years old. Okay. And it goes down here, and this is not a small device. It's a substantial device. And so it actually describes the whole thing and has good descriptions of the various components and how they fit together and how they are machined. So I think there is a realistic possibility that we can make a version of this device and apply the learning from the Kladov patent, which is now being translated, and potentially produce a heat generating reactor. Okay. So it's all defined there. Figure 1 schematically shows an ultrasonic activator in which the proposed method can be implemented. Figure 2 and 3 represents the diagrams of experimental setups for implementing the proposed method. 4 and 5 show a graphical dependence of the amount of energy released from the magnitude of the variable and static pressures. Figure 6 and 7, graphical dependence of gamma and beta radiation On the composition of the process substance in the implementation of the proposed method, Figure 9 shows graphically the dependence of neutron radiation on the operating mode of the setup shown in Figure 3 and on the distance between the neutron detector and the ultrasonic activator in the implementation of the proposed method. No, he did not look for elements. No, he did not look for element isotopes and gas isotopes. But he did what was possible for him, which was to use the expertise in monitoring nuclear radiation that was there in the Soviet Union to absolutely nail that this is a nuclear process that is going on. The processed liquid, for example water, is fed into the ultrasonic activator schematically depicted in Figure 1. I can maybe bring that up in a different window. Let me just get that up so you can see it whilst I'm talking. I have it in there, but right, so we'll put Figure 1 over to the side so you can see it at the same time. In theory. Yeah. Okay. All right, so Figure 1's going to be over to the side here. The ultrasonic activator contains 2 or more working chambers. So there is a working chamber, and that is 1. That's the working chamber there, 1. Connected in series. There are 4 in this example. 1 working chamber, 2 working chamber, 3 working chamber, 4 working chamber. In each of which there are impellers, 2. That's an impeller there, connected to the drive shaft of a centrifugal pump are installed with rotors 3 fixed on the periphery in the form of a perforated rings. You can see that in the patent over here. These are the impellers, and they've got perforations down them. Okay. Coaxial to the rotors 3, in the cases 4 of the working chambers 1, opposite each rotor is a stator. So there's a stator here made in the form of a perforated ring. The working chambers 1 are interconnected by means of diffusers 6. The last working chamber is connected to the first chamber 1 by a circulation circuit. So it goes out here and back in here, out here and back in here. Okay. The ultrasonic activator operates as follows. During rotation, the impeller 2 of the centrifugal pump gives kinetic energy to the fluid being processed, which is partially converted into static pressure in diffuser 6, and partially into alternating pressure when passing the perforations of rotor 3 and stator 5. Depending on the selected fluid, its temperature and the calculated values of static and variable pressures that satisfy the above dependencies, the design and technological parameters of the ultrasonic activator are established and maintained in this patent here. Okay, so you can go and look at that. So that's that diagram again we see down there. During the action on the liquid of the half period of the negative half wave of alternating pressure in the liquid located in the treatment zone, cavitation bubbles form. During the action on the liquid of the next half cycle of positive half wave of variable pressure, cavitation bubbles are compressed. By the end of this half cycle, the bubbles store kinematic energy, which is determined by the pressure difference acting on the bubbles from the outside and from the inside. Outside, the sum of alternating and static pressures acts on the bubbles. Inside the bubbles, the pressure of the saturated vapor of the liquid acts. In addition, other forces determined by the physico-chemical properties of the liquid and the absolute values of the parameters to be measured also influence the movement of the bubbles. At the moment the bubble disappears, at the moment of its collapse, the kinetic energy is converted into the collision energy of elementary particles. The energy released during the collapse of the bubble is several orders of magnitude higher than the binding energy of elementary particles, nucleons, in the nucleus. As a result of the collision of nuclei in the conditions of the proposed method, an interaction occurs between elementary particles of the constituent nuclei. The energy released in the reactions controlled by the described method between elementary particles is converted into thermal energy in a liquid, and it is removed from the treatment zone with a liquid stream. So basically a heat exchanger. Okay. In specific examples of the implementation of the claimed method, experiments are described that are performed in experimental installations with open and closed cycles, figures 2 and 3. So this is an open cycle, and this is a closed cycle. So in the open cycle, effectively, you're pulling the liquid in, it's going through this 4-stage device, it's heating up, and it comes out, and the hot water is going out and used somewhere else. In figures 3, it comes out of this accumulation vessel. Maybe this is chilled so that it doesn't change the parameter space. Comes in, does its cavitation, comes out hot, and then the same water is chilled and then sent back round the loop. The reason this is done in figure 3 will be explained later. Okay. The installation shown in figure 2 contains an ultrasonic activator 8. So I'm going to show a different image here so that we can follow this along. Okay. So the ultrasonic activator is 8. That's the thing you've just seen before. The description of which is given above. An electric motor 9 here for activating the activator. A power meter 10 for measuring the power here. A device 11 for measuring the temperature of the process fluid. 11 here. This is the process fluid at the input and output. So input and output. A radiometer 12 here for measuring gamma and beta radiation with the radiation detector 13 here. A neutron radiometer 14 here for measuring neutron flux with the neutron detector 15. A manometer 16 there's the neutron detector, so 14 here and 15 here. A device 18 for measuring liquid gathering device, 19 for measuring the frequency spectrum of variable pressure. A valve 20 here and here is installed on the pipeline discharging liquid from the installation. Valve 21 is installed between pipelines discharging and supplying liquid to the installation. Okay. So the installation works as followed. Liquid, such as tap water, is piped to the inlet of the installation, so here. The valve 20 sets the amount of water flow passing through the ultrasonic activator 8. So that 20 here, the amount of water going through 8, where they support the above calculated ratio of variable and static pressures. To change the static and variable pressures within the specified limits, valve 21 is used. So this valve is changed to allow some pass-through of water to change the pressure variation between the input and the output. Having established the necessary operating mode of the installation, they are allowed to stand for 10 to 15 minutes to achieve stable operation at a given mode and make the necessary measurements. The power consumption N1 is measured by a wattmeter 10. The heat generation power N2 is determined by the product of two measured quantities. The difference, delta T, of the temperature at the inlet, here and here, the inlet and the outlet of the activator 8, so the outlet here and here, measured using the device 11, and the flow rate G of the fluid passing through the activator 8, measured by device 18. This is the flow rate meter here. Okay. And the heat capacity constant of the treated fluid. So N2 equals delta T times G, the flow rate, times the heat capacity constant in watts, and that's equation 1. Instruments 16 and 17 for measuring pressure are used to monitor the operation mode of the installation. The frequency spectrum of the variable pressure is measured by spectrometer 19. Using radiometers 12 and 14, so 14 14 here and 12. 14 here and 12. The fluxes of ionizing radiation are measured. After all of the above measurements, we can conclude that the power consumption for the implementation of the proposed method is on average 2 to 3 times less than the heat output released as a result of the proposed method. That, my friends, is exactly in line with the observations of Bin-Juine Huang. Moreover, ionizing radiation released during the implementation of the proposed method does not exceed the natural background. That, my friends, is exactly in line with the observations of Bin-Juine Huang. To confirm the existence of nuclear reactions in cavitation bubbles of the treated liquid and the formation of gamma and beta and neutron radiation when implementing the proposed method, the installation shown in figure 3 is used. This one here, the lower image here, which I will go in and we can look at a little bit more specifically. This installation is made similar to above described and depicted in figure 2 and differs from the latter in the presence of a container 22 here for the accumulation of these radiations to a value that can be measured by available instruments, right? The accumulation of these radiations. Now, it's going round in a closed loop. What we talked about earlier is that in later research, Kladov processed for, let's say, 360 hours and saw the synthesis of 55 elements or whatever it was I showed you earlier. So the longer it goes on, you've got more fissioning, more fusion, more transmutation, and more complete collapse of matter. So that is also in line with what we see in our ultra experiments, that the longer you run those, the heavier elements you seem to be synthesized, but it's limited by the thickness of the aluminium foil. We appear to have seen silver synthesized, which is the heaviest element we've seen in the experiments that I've done. Potentially, it could be a lot higher, but you don't want to push it too high because in the case of Leclerc, he was using thick aluminium perforated sheet in a Swiss roll, and he was generating transuranics. You do not want to be doing that, okay? So what Kladov was doing in this experiment using here, the recirculating thing is, let's say you're starting off with oxygen 16, stable. Oxygen 17, stable. We've added a synthesized neutron. Oxygen 18, stable. We've added a synthesized neutron. Oxygen 19, well, that decays, producing fluorine 19, doesn't it? So that gives us a understanding that as you are increasing the mass of certain original isotopes, you might end up into a situation where it has several stable steps, but if you keep working at it, you end up by producing some radioactive elements. And that is deliberately what he's done in this process. So again, he says, this installation is made similar to the above described and depicted in figure 2 and differs from the latter in the presence of container 22 for the accumulation of these radiations to a value that can be measured by available instruments. The fluid in this case circulates in a closed loop between the ultrasonic activator and the vessel 22, ultrasonic activator and the vessel 22 for as long as it takes to accumulate a level of radiation that is measurable. Okay. To more clearly confirm the occurrence of nuclear reactions in cavitation bubbles of the liquid being treated, additives of stable isotopes, oxygen, nitrogen, carbon, sodium, were used, which, as a result of nuclear reactions occurring in activator 8, turn into unstable isotopes, which was recorded using radiometers 12 and 14. This, my friends, is not just an energy generation patent. It is systematic science used to prove that cavitation in water with additives are doing nuclear level reactions. Thus, when implementing the proposed method, it becomes possible on an industrial scale to obtain the energy of strong interaction of elementary particles. And this is without having to go and refine ridiculously expensive and rare isotopes of particular elements and go and find particular resources in difficult places, using difficult methods. This is using iron, extremely abundant, motor, those two things combined into a structure and flowing water through it, essentially. And a little bit of control and some valves, right? Obviously, I don't want to dismiss the incredible work that must have been done by Kladov over many, many years to achieve at this end point. But we're at the point now with the project where we can see a way forward to produce working embodiments, and every effort needs to be made so that the absurdity that is going on can be put to bed. Example 1. The strong interaction energy of elementary particles formed in tap water at temperature of 20 degrees is obtained. This water is at this temperature has a tensile strength of approximately 0.35 megapascals. The pressure P3 of saturated vapors at the indicated temperature is approximately equal to 0, i.e., I guess it's below 0. The water isn't boiling, so okay. So by dependency, P1 equals 0.3 times P2 plus P3. P2 plus P3 minus P1 equals... So this is what I worked out by looking at all of the different papers. And for some reason, it's not showing that properly. So give me a second. I don't know why it's not doing that. It should be doing that properly. Okay, it's doing it properly now. Don't ask me why. So essentially, P2 equals sigma over 0.7. I worked out from the mess in those two available patents what this should be. So, like, is it that bar? Yeah, this is kind of what I had to go with here. Total nonsense. Just not telling you what it is. It's like, what is going on here? Please, can someone tell me? Right. So there's no equal sign in there. There's no bracket. It's missing the P3. There should be a minus in here. I don't know. It's just a total mess or whatever. Like, I mean, it's just a total mess. And in the actual other patent drawing, text, it's better. And between the two, I managed to work it out, and then I verified by doing the maths. So in here, we have the same thing going on, except it says P2 minus 0.3. P2 equals sigma, and it's like, what is this equals? And then down here it's got minus. That is equals. Is it minus? Anyway, I managed to work it out, and I verified the maths, and I basically got it here. So basically, if P1 equals 0.15, P2 equals 0.5, and P3 equals 0 because of the temperature of the water, and the water is the working fluid, then all of these things are valid as per the equation. So I've done the hard work. So these are the parameter spaces that need to be fulfilled to achieve moving into excess heat. Okay. Tap water at a temperature of 20 degrees C is fed into the ultrasonic activator shown in figure 1. Let me bring that up again. where by acting on valves, we're going to do this one here, where by acting on valves 20 and 21, 20 and 21, shown in figure 2, or this is figure 3, it's basically the same, using measuring instruments 16, 17, and 19, the variable and constant pressures defined above can be established. When passing tap water through an ultrasonic activator, the water is heated as a result of strong interaction of elementary particles. Heated water is removed from the activator and sent through the pipeline to the consumer of thermal energy. After transferring thermal energy to the consumer, the chilled water is either discharged into a sewer or returned to the activator for reuse. Using a wattmeter, 10, the electrical power consumption N1 to realize the proposed method was measured, which was equal to 6 kilowatts. The power produced N2, according to the above expression 1, in this case is equal to 6.5 kilowatts. Dividing the electric power consumption N1, which in this case is 6 kilowatts, by produced power N2, which is 6.5 kilowatts, a coefficient of 1.08 is obtained. So when you exactly meet this threshold for water, and it's done it again, I don't know why it does that. When it exactly meets this threshold, then you get over unity. And this 8% is in line with some of our lower levels achieved when replicating the Celani wire. So that is the kind of baseline test here. Examples 2 to 12. So here's the table. I need to translate the table. But essentially, these were performed in a similar way to that described in example 1. The substance consumption, the substance under processing, its temperature, treatment, and parameters P1, P2, P3, and sigma, power consumption N1, and heat output N2, and coefficient K are given in table 1. Now, this is where we get a real gift from Kladov. So the first experiment we showed, 1 was water, and it had, with its parameters, an excess of 8%. Now, in this 2 through to 12, this Russian word, this means substance, and this Russian word means water. And so from 2 to 12, they are all water. The input temperature varies from 28, 29, 24, 24, 21, 20, 22, 22, 26, 22, 22. P1 is 2.4 roughly, or 2.5 mostly, with 2.3 down here. P2 is 6.7 through to 40 here, and the 40 is the highest at 20 down here. P3 is 0 throughout because the input temperature is below the boiling point of water. Sigma here is mostly, in fact, in every case, it's 1.2, which is the working parameter. And we can see here the input energy in kilowatts. This is not a small device, my friends. 124.8 kilowatts, 88.8 kilowatts, 123 kilowatts, all the way down to here, which is 122. So the highest one here is 127 kilowatts. But the output in thermal energy is 265 kilowatts. And in this case, where the excess heat with water, with a input temperature of 22 degrees, P1 of 2.3, P2 of 23.3, and P3 of 0 and 1.2 on the sigma, is 6.46. That is 512.1 kilowatts. That is an excess. I mean, what's that? 80 away. That's 530 something. 533, 534, 534. That's half a megawatt of excess energy. Why isn't this implemented everywhere? Why? Why isn't it implemented everywhere? That's half a megawatt of electricity, of heat rather. That means, like, if you could do this on a smaller scale, you could put in half a kilowatt of solar power from a Didi solar array, put it into this system, and get 3 kilowatts of output energy, which is enough to heat an average kind of home. Boom! A small solar array heating a large home. or you could double up on your solar array so you could get the same level of heating in the winter. That is something that is a killer application if this scales backwards. These are big devices. He's not joking when he says this is an industrial heat generator. Okay, now here is the kicker. What is this 5% here? I'll do the translation again. Hold on, no, I won't. I think I've already done it. I need to translate those particular slides, this table rather. What is added there in experiment 13 is I'm just doing the real-time translation here. I think you'll find it's sodium silicate. No, it's aluminosilicate suspension. He has added aluminosilicate suspension, 5%, to the water. He's running the input temperature at the lowest kind of temperature. He put it in at 20 degrees. The P1 in this case is 1.1. It needs to change because you're changing the properties of the water. P2 needs to change because you're changing the properties of the water. Sigma changes because you're changing the properties of the water. But in this case, with just the additive of this cheap, abundant 5% aluminosilicate, you get an input power of 72 kilowatts and an output power of 836 kilowatts. That is 11.61 COP. That is, if you get a good heat pump, right? You've got optimum temperatures outside, driving optimum temperatures inside your house, and you, let's say, get a 3.5, maybe 4. This is getting on for 3 times the maximum efficiency of a heat pump. And it's in theory, it's quite a simple device compared to a heat pump. And in these cases here, there is no radiation. No perceptible radiation beyond background. No perceptible radiation beyond background. Okay? This, to me, is a real direction for exploration. These experiments here, 1 to 12, validate the observations of Bin-Juine Huang. When I suggested Bin-Juine Huang, I hadn't been able to see the paper, but the people that I saw that were reporting on it were people that I trust, and it was an awarded patent, and it made these claims of producing very clear over unity signals. I wasn't aware that it was in the hundreds of kilowatts of excess heat, right? Hundreds of kilowatts of excess heat. And I wasn't aware that he had also observed no radiation in those instances. I also wasn't aware that he added a simple compound. Now, why would aluminosilicate allow for the synthesis of excess heat to such a high degree? Well, it could be because, using the Parkhomov reaction tables, if we start with aluminium and we synthesize iron, we get 21.8 million electron volts. And of course, what do we see in our ultra experiments? We see aluminium fusing to iron. Here again, aluminium and silicon are both in aluminosilicate fusing to iron 56. It is the perfect additive. It is the perfect additive. This is not guesswork. This is the result of knowing what you are doing. Okay? This is the result of him knowing what he was doing at the end of a long research period. Okay? You've got exchange reactions as well here. Aluminium and silicon, silicon, so on, to iron reactions with the production of helium or hydrogen. Of course, for each isotope, the ones that, in my view, are most likely to have happened at the top of the table. Okay? But we already know that we see silicon produced in ultra experiments. We already know that we see iron produced in ultra experiments. So it stands to reason that he's done his homework, and there's a good reason why. We know from the carbon arc underwater experiments of Sundaresan and Bokras in the mid-1990s that it synthesized iron. And I'm arguing that it is because it was the same magnetohydrodynamic structures that are caused in this arcing underwater with oxygen as a key. So, very simply, we have an opportunity here to explore increasing the excess heat of Bin-Juine Huang by the addition of a 5% in aluminosilicate, and by learning how to achieve these parameters for knowing that you are getting into the sweet spot that allows for the cavitation bubbles to be forming at the right size and for them to be compressing at the right kinetic velocity. Right. So, with that aside, we can talk about more detail on the radiation measurements. So, the table shows that when processing various substances in the liquid phase at certain variable and static pressures lying within the specified limits, i.e. when implementing the proposed method, the energy received is several times greater than the energy consumed. We like that kind of phrase, several times greater than the energy consumed. Now, figure 4 here, the graph shown in figure 4 shows the dependence of power difference, delta N, of heat release and power consumption on the ratio of constant and alternating pressure in the activator. Said dependence was determined by the present method, using tap water at a temperature of 20 degrees C as the treated substance. I'm going to pull this up so you can see it separately. This is figure 4. Okay. The graph shown in figure 4, blah, blah, blah. The variable pressure is plotted on the x-axis here, and the power difference, delta N, is plotted on the y-axis. Curve 1 on the graph corresponds to static pressure P10, curve 2 to P1.6, curve 3 to P1.8, and curve 4 to P1 megapascals. P1 equals 1 megapascals. From these graphs, the boundary of declared interval of the ratios of variable and static pressures is clearly visible. Everything that lies to the left of 2.3 megapascals for graph 1 here, this is graph 1, everything to the left of 2.3, somewhere here, does not satisfy the proposed pressure ratio P1 and P2, and the amount of energy released is less than the amount of energy consumed. With an increase in variable pressure P2 more than 2.3 megapascals, i.e. subject to specified ratio P1 and P2, the released energy is greater than the energy consumed. So when you get over here, the energy is in excess, but not very much, right? Okay. For graph 2, this one, where static pressure is 0.6 megapascals, everything to the left of 1.2 here, everything to the left of 1.2 here, does not satisfy the proposed ratio, and the amount of energy released is less than the amount consumed. Similarly, by extrapolation, you can see the other ones follow. So this is a very systematic study. It's a very systematic study where he's proven the ratio necessary to produce the right type of bubbles as a generalized solution for all forms of liquid in the reaction zone using cavitation process for reactions in the nuclear domain. Similarly, by expression, blah, blah, blah. Figure 5 shows a graphical dependence of the difference in power, delta N, here, heat and power consumption from ratio of P1 and P2 when implementing the proposed method in a device of lower power. Graph 5 here corresponds to the static pressure P1 equals 0.1 megapascals, graph 6 to 0.2, and so forth to 0.5. Okay, so when you have the ability to increase the pressure, you get to the possibility of creating higher and higher yields. This kind of stands to reason. But of course, in the resonant phenomena of the ultra experiment, we are building and building and building the oscillating energy at a particular zone. And so it's not unreasonable to expect that to achieve total destruction of the matter and nuclear interactions. And I'm arguing it does both the construction and deconstruction on one another sides. From these graphs 5, 6, 7, 8, and 9, as well as from graphs 1, 2, 3, 4, shown in the figure 4, it can be seen that only when specified ratio of P1 and P2 is fulfilled, the released energy is greater than the energy consumed. This is knowing, I repeat, this is knowing how to create cavitation heat generation systems. Not guesswork, this is knowing. The released energy is greater than the energy consumed. Moreover, for graph 5, it is seen that to the right of the value P2 equals 26 megapascals, i.e., if the above ratio is not observed, the released energy becomes less consumed. Okay, so that is in 5. Yeah, so in this particular case, if it goes over a certain ratio, then you start dropping below 0 again. So you need to be within this bounds. It needs to be within this bounds. It's brilliant work. It's absolutely brilliant work, but it's about to get a hell of a lot more brilliant. William Schwant is saying the step 1 is to making smaller and smaller bubbles at a certain ratio. No. It's very well described. You need the right type of tensile strength in the liquid. You need that taken into consideration, which is affected by the liquid type. You need to consider the vapor saturation pressure and so forth inside the bubble, and you need to consider the size of the bubble and the pressure and the combination of the vapor pressure and the tensile pressure, and all of those factors together. And if you go outside of the parameter space that he has calculated through a hell of a lot of research. This must have been a hell of a lot of research conducted over many, many years. He has defined if you go outside of a ratio, you do not see excess heat. If you go under a ratio, you do not excess heat. You need to be within this generalized band, which can be calculated for any liquid substance. It's absolutely brilliant. Right. So, figure 6, which I shall bring up here so you can see it as we talk through it. Yeah, maybe. Since the proposed method of obtaining energy is characterized by the practical absence of ionizing radiation. Yes, that is what we like. We like large amounts of excess heat. We like 10 times the energy out that we put in without any ionizing radiation. That is what we like. Yes, we like that a lot. To confirm, for those people that might not believe this is happening, the occurrence of nuclear reactions in cavitation bubbles, we processed liquids in figures 6 and 7. Graphical dependencies of gamma and beta radiations are presented for the treatment of tap water at a temperature of 20 degrees C with various additions of stable isotopes of various substances. The y-axis gives the average value in the number of gamma quanta and beta particles in 1 second here. Okay? So here we are seeing, in this variable chart here, we are seeing 1 sample per second of gamma or beta, and then up here it goes to 2.5. And here it goes to 14, right? From less than about a half to 14, or a quarter to 14. That's a huge change. The recorded by the detector 13 of the radiometer 12, figure 2. Averaging is given for each hour of measurement. So each of these spots is that level of radiation for an hour. Okay? The x-axis shows time t in hours and days. In addition, the x-axis in figure 6 and 7 marked time tau here of the ultrasonic activator. So this grey bar here, this hatched bar, is the time that the activator was running. Thus, Schedule 6.1 shows the relationship of gamma and beta radiations with tap water treated at 20 degrees C with adding air. That's mostly nitrogen, some oxygen, extremely small amount, 0.004% of carbon dioxide, and a little bit of argon and trace. In the amount of 1.8 times 10 to the minus 6 kilograms per second in accordance with the proposed method. The Schedule 6, so that is here. So you can see by adding air, okay, there's a slight increase over the activity. When I say slight, it goes from, you know, being down at about a quarter count per second through to 2.4 during this operation. And this is by the reactor implementation where they are cycling it around. So they're deliberately trying to build nuclei that are unstable, okay? By, one might argue, repeatedly adding nuclei to other nuclei, okay? So that is air. In accordance with the process. The Schedule 6.2, the same with the addition of air in the amount of 3.6, so that's a doubling. So it didn't really make much difference when you have, you know, 1.8 times 10 to the 6 or 3.6 with air, right? Schedule 6.3, the same with the addition of air in the amount of 0.9. So when you add a little bit, okay, you seem to get a bigger effect, okay? So maybe by adding too much air, you are changing, you might be dissolving nitrogen in there, and it actually lowers the activity that you can achieve. This is interesting because this is in line with the findings of Sundaresan and Bokras. Because if you add more air to there, you're going to be adding a lot more nitrogen. Is this inhibiting the process? Certainly, of the three that have air, the one that produces the most has the least. So 0.9 produces the most radiation. 1.8 less, looks almost like half, and then almost looks like half again when you have 3.6. Okay, so adding air reduces the radiation. Okay, or maybe the air in there is actually capturing synthesized neutrons for some reason, or maybe it's oxygen that's in there that is capturing, I don't know, but it would appear to be that the less air you have, the more signal you get, okay? Schedule 6.4 is the same with the addition of carbon dioxide. Now, he doesn't specify where this carbon dioxide comes from, but it's 2 times 10 to the minus 6, so it's somewhere in between these ranges, and it doesn't seem to change much. It almost doesn't change at all, okay, during that period. But in Schedule 6.5, this one, is the same with the addition of carbon dioxide in an amount of 10 to the minus 6 kilograms per second. I've looked at all of the versions of this patent, and it doesn't specify the amount, it just says an amount. So it's not being disclosed how much is being put in there, but it produces a vast quantity of increase in the radiation. And it has this very long decay curve. Okay, so I wanted to find out what this decay curve could mean. And I found out that between this point here, this sample point here, and this point over here is an 8-hour period. Maybe I can show you the chart where I defined that. Not that one. This one. So I stretched out this part, and it says in the text that these are days and that these are sample points of hours, and so I averaged over the hour, and so I worked out that this is 8 hours between this sample point and here. And then I thought, what possibly could be producing this half-life decay, and what could be producing it from the addition of carbon and oxygen. So if we go to here, It's carbon dioxide, but of course it'll be smashed up and there'll be carbon and oxygen in there. And we know that carbon and oxygen like to fuse. What could it possibly be fusing to? If we do this and we go nanosoft.co.nz and we go fusion reactions here, and I type in, I'm just going to make this bigger for you. I type in carbon and oxygen, and we'll do that again over here. What do we get? Well, we get for the carbon and oxygen we get, that's interesting. This one here. We get carbon and oxygen is phosphorus 31, but we need to have a neutrino on the right, which means that this is producing silicon 31. Okay. So what does silicon 31 produce? This is not in Kladov's patent, but I felt it was necessary to try and understand what that decay is referring to. So, if we go to this lovely site here, which is the nuclear structure and decay data guide here, and we zoom in and we look at silicon 31, we can see it has betas up to 1.492 kilo electron volts with the mean energy, or the biggest energy of 595. This would be easily detectable out of the device. Okay. So there it is. The beta is 595, and the half-life here, it's 100% beta decay of silicon 31, and it decays to phosphorus 31. This is something that has been observed in these systems, and so 157.24 minutes. Well, I did the maths on this, and it turns out that if you have, what I did was I looked at this and I saw that this is 1.4 here, and that this is roughly 11.6. Bearing in mind this is coming off a, odd type of not highly accurate and scanned image. But anyway, this is roughly 11.6 here, and 8 hours later the counts per second has dropped to 1.4. And if we are to assume it's all beta, because it is all gone to silicon, let's say this is silicon 31. Here is the 0 to, this is 11th hour in the day and the 19th hour in the day. And this is 0 hours to 8 hours. So this is 0 minutes to 480 minutes. The half-life is 157.24, so you divide 480 by 157.24. That is equivalent to 3 half-lives, okay? So the original is 11.6, and then this is 1.4. So if you divide, I've just done this by 3 half-lives, because it's gone through 3 half-lives, and it's actually slightly over 3 half-lives. So I've only done 3 half-lives here. I get to a figure of 1.45. So if I added this extra bit of half-life in here and considered the not perfect estimate of the input here, I think that what was produced is the fusion, and I'll just pull up precisely what the fusion is here. It is this. If I can zoom that up there, and I will put this all in the blog. It's the fusion of 13 carbon plus 18 oxygen, 13 carbon being 1.1% of natural carbon, and the and 0.204% is natural 18 oxygen. This fuses to 31 silicon, and this decays to 31p in this 157.24 minutes with a beta of that up to that, and this produces our output, okay, which then it could also be produced from 14 carbon in the air, or if it was produced from an organic source, the carbon dioxide, and 17 oxygen, which means that, as you know, when you are doing this process, it would appear that we are synthesizing 17 oxygen. And as I said at the beginning, Alexander Shishkin observed an increase in 18 oxygen produced in his cavitation device. Therefore, if you are also taking 12 carbon and putting a neutron in and getting 13 carbon, or 13 carbon and putting 14 carbon in, the longer you run this with carbon in the situation, you are going to end up by producing an increasing amount of silicon-31, and this will lead to the observed decay rate as verified from the data that was in the paper. And therefore, I think that this decay here from the addition of carbon dioxide is due to the synthesis of silicon-31, which confirms fusion of carbon and oxygen. This confirms the fusion of carbon and oxygen. And additionally, it would indicate his other reaction confirms the fusion of silicon and aluminium to iron. And these are the kind of things that are going on in the thunderstorm generator. And as I'm saying, this is actually producing magnetohydrodynamic structures, and so does anything that's producing ball lightning like structures. So I think in a way this also confirms the thunderstorm generator. It's extremely good work. Posthumously, I think he died in 2003. This is a great loss. It's a great loss that he didn't get recognition for this work during his lifetime, but he's certainly going to be given a forum if I have anything to do with it. Okay, so 6.5. Therefore, I believe this is almost certainly just beta radiation that is being observed in this instance, and it is due to the synthesis of silicon-31, which decays in the half-life as represented by the half-life you can see in the hours after the running of the closed cycle cavitator. Okay, now blah 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 blah. Okay, graph 7.1, which we shall look at now. Figure 7 reflects the dependence of gamma and beta radiation detected in the detector 13 on the residence time of the latter in the core. Figure 7 shows the dependence of gamma and beta 7.2, radiations with tap water treated, blah, 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 with carbon dioxide in an amount of 4 times 10 to the minus 6. Graph 7.3 here, the same with the addition of carbon dioxide in an amount of 2 times 10 to the minus 6. So here we go, we've got it going up again, and so on. So what this means is potentially that if Bin-Juine Huang runs his reactor in closed loop mode and deliberately adds carbon dioxide, there is the potential for observing a 157 or so minute decay from silicon 31, and that will be absolute categorical proof that nuclear reactions are occurring in his device. Okay. Of course, you know, the counts per second is going from 1 in this case to 8.5. And because the energy of it is, the mean energy is 595 kV, you could provide shielding to cope with this to a degree. That's quite high energy, but anyway, it's beta, so it will be stopped relatively quickly. And you might actually be observing Bremsstrahlung radiation from that beta as it interacts with the metal. So it doesn't matter whether it's Bremsstrahlung radiation or it's actually beta itself. It's due to the beta, in my opinion, because we are seeing, again, in figure 7 here, we are seeing a similar type of length of decay as we saw here. So in my view, this is the synthesis of silicon-31 decaying with a 157.24 minute beta average energy 595.638 keV. Okay. Now, in this last part of this chart, he is showing in 7.4 reflects the dependence of gamma and beta radiation without activating the ultrasonic activator recorded on the surface. The activator indicated by the dots at a distance of 13 meters from the activator. And graph 7.5 is the same as graph 7.2, but with the addition of carbon dioxide in the amount of 16 times 10 to the minus 6, and the dependence of gamma and beta radiation recorded at the distance of 13 meters from the activator. So, of course, 7.3 had a higher signal here, so you probably don't want to add too much. It's about adding the right amount, okay? But what they're showing here is that during this process, when you have a gamma and beta detector further away, you see these areas here. Maybe I've zoomed in there. This is when you've got the detector right next to the cavitator, and this is where you have the detector at 13 meters away. You cannot see the signal. So this is saying that you are completely safe if you are 13 meters away from this device. In line of sight, I would imagine. So if you are operating this in a mode in which you are trying to detect the decay product beta and possibly Bremsstrahlung gamma from, or rather Bremsstrahlung photon radiation from the decay of the 31 silicon to 31 phosphorus, you will be safe conducting this experiment when you are 13 meters away from it. Okay? That's very important for people conducting this experiment with the aim of proving that it is a nuclear process that is going on in the reactor. Okay. The graphs shown in figure 6 show that when the ultrasonic activator is switched on, i.e. when water is treated at 20 degrees C and the ratio of alternating and constant pressures is within the specified limits, there is an increase in gamma and beta radiation, which is only possible during nuclear reactions. Which is only possible during nuclear reactions. This data is saying 100% certainly that this is doing nuclear reactions. Similar studies were carried out when sodium carbonate, Na2CO3, gasoline, lithium, chloride, and other substances were added to tap water. The results of the recorded gamma and beta radiation are similar to those presented in figure 6 and 7. Right. This is neutron radiation. The increase in neutron radiation, which confirms the occurrence of nuclear reactions in the implementation of the proposed method, is illustrated in figures 8 and 9. So, figure 8 depicts a graph of neutron radiation of the natural background for several hours. So this is nothing going on particularly. So neutrons per second is less than... always less than pretty much less than 0.05 neutrons per second. The neutron flux in neutrons per second is marked on the y-axis here, time t in hours on the x-axis. So these are probably averaged at these sample points. Okay? This does not look like this. This is in the 0.01 to 0.05 range. This is in the 1 to 70 neutrons per second. 70 to 1 to 70 neutrons per second. Okay? That's a lot more. In figure 9 is a graph of neutron radiation during operation of an ultrasonic activator, i.e. when implementing the proposed method and observing the ratio of variable and static pressures when processing tap water with a temperature of 20 degrees C, with the addition of lithium chloride. Figure 9 also shows 3 periods, this one, and this one, indicated by the time T1, T1, T2, T3, or tau 1, tau 2, tau 3, during which the detector 15 of the neutron radiometer 14 was installed at a distance respectively of 0.5 of a meter, this one, where you can see that the neutron counts here when it's at 0.5 of a meter is round about 5, which, given the fact that it was less than 0.05, is 100 times greater neutron flux than background when it's at a distance of 0.5. When the device is at 1.25 meters away, the neutron flux goes to about, let's say, peaks at around about something like 3. Okay, so again, it's still, you know, much more than 1 order of magnitude more neutrons. But at 3.2 meters from the surface of the ultrasonic activator here, the neutron flux is just around about 1. It doesn't drop below 1, and in that case, it is, let's say, 20 times greater than the background dose. So would I want to stand 3.2 meters away, or would I want to stand right next to the cavitator when it's outputting, let's say, here, 50 neutrons, which is, you know, absolutely ridiculously scary levels. It's 2 full, 1, 2, 3 orders of magnitude more neutrons. No, no, thank you. I don't want to be there. I want to be there or further back. So the implication here is that if you were to conduct these radiation experiments and be 13 meters away, given the fact that this is 3.2 meters away, then you should be relatively safe. Although, don't try this at home, kids, if you're not experienced with nuclear radiation. Okay? Right. So that's that. When comparing the graph depicted in Figure 8 with the graph depicted in Figure 9, it is seen that the neutron radiation during operation of the activator is significantly higher by several orders of magnitude than the natural background. This once again indicates that when implementing the proposed method in the cavitation bubbles of the treated fluid, nuclear reactions occur. What nuclear reactions? What nuclear reactions? Okay, well, possibly the nuclear reactions, if we go back to here, and I think that what is going on, if I can zoom down here, so if we go down to lithium down here, and we go to lithium 10, okay, lithium 10 decays 100% of the time with a neutron. Okay, so I think probably that lithium 7 is going through a lot of jumps to lithium 10. I can't find anything with chlorine. I can't find anything with fusion of lithium and chlorine, and fusion of chlorine and chlorine and lithium chlorine fusing goes to calcium isotopes and so on. The easiest way that I can see of synthesizing something that produces 100% neutrons with lithium in play is the synthesis of lithium 10, and this would, given the fact that it has a lithium 10 has a, if I look at isotopes of lithium here, a new tab, if we go to isotopes of lithium here, and we go to lithium 10 here with its neutron, This decays in not a lot of time. Two I don't know, zettoseconds or something. It's like so ridiculously small. Basically instantaneously. So as soon as it's made, it instantaneously decays. It goes to 9 lithium, which decays in 178.2 milliseconds, which goes to 8 beryllium. And I think 8 beryllium will probably decay into 2,4 helium. I think that's what will happen. So you'll probably get some 4 decays to 2 alpha particles. Yeah. So basically, as soon as this is made, then it decays. So the 10 lithium, we get our neutron, and then it in 178.2 milliseconds. But you can see here that if you add a neutron to lithium-7, that lithium-7 hangs around for 838 at 8.7 milliseconds. So you might be able to get another neutron in there, and then the lithium-9 hangs around for 178. So this is 838 milliseconds, and lithium-9 hangs around for 178 milliseconds. So that's probably long enough. But as soon as you get 10 lithium, that instantaneously decays, right? So, and that goes back to 9 lithium. So you've basically got a cycle between these two. And if it hangs around long enough to decay, then it will actually decay to 8 beryllium or 9 beryllium. And if it decays to 8 beryllium, which is half of the time, you'll get some helium production. Okay? So that is my assessment. The good news is here that by adding lithium, the neutron should be observable, but it doesn't. The radiation doesn't hang around for very long. In fact, it's imperceptibly short. Basically, as soon as you turn the device off, this will all decay back to either 9 beryllium or 8 beryllium, which will then split into 2 helium nuclei, alpha particles. So that's good news. And if that is true, and it is this neutron that is the result of the neutrons that are being observed here, it means that essentially, other than neutron activation of the reactor, it would be relatively safe to conduct this experiment just to prove that the reactor is doing a nuclear reaction. Okay? So this for me is stellar work. Absolutely stellar work, confirming with precise additives that you can add into a system that's actually doing the work. So if Bin-Juine Huang's system is complying with the parameter space that is being defined by Kladov, which it in theory must be in order to produce excess heat, and he can basically essentially always produce excess heat, and he says typically it's around about 1.6, which is well obviously within this range that qualifies. Then one, he can add the aluminosilicate compound to it to potentially extend that excess heat to a far greater level. Two, add carbon dioxide at some level in order to observe potentially, which I think is this synthesis of silicon 31 and decay to phosphorus 31 with this 157-minute signals that can be picked up by beta gamma detector, and the addition of lithium chloride to produce the signature of neutrons. And I think that will be just the whole thing will be totally settled. It'd be like, anything else to whinge about? Right? So thank you Kladov, for this incredible piece of work here. And I'm just gonna we're basically at the claims here, and you'll see that the claims are basically for a generalized solution to producing cavitation systems that yield excess heat through nuclear energy processes. Right. So when comparing the graph in figure 8 with the graph in blah 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 blah. Similar studies on neutron radiation were also carried out when other components, for example, gasoline, were added to the liquid to be processed, which made it possible to increase neutron radiation to a level that can be measured with existing instruments. These studies have led to similar results. Thus, the use of the proposed method allows on an industrial scale to obtain the energy generated as a result of the strong interaction of elementary particles of the processed substance. The easiest way to use the proposed method on an industrial scale in the field of heating and hot water is in the field of heating and hot water supply for civil and industrial facilities. For this, it is necessary to connect the device for implementing the proposed method to the heating and hot water supply system of the facility, for example, in heating distribution pumping stations. Using the proposed method is economically advantageous because, firstly, in this case, the capital costs are reduced to almost zero. There is no need to build boiler rooms, fuel deposits, access roads, transport pipelines, and much more. Secondly, the amount of energy produced is several times higher than the energy consumed. Thirdly, the environment is not polluted by fuel losses during extraction, transportation, and its combustion products. And this is the simple claims of the patent. I love it when a patent has such simple claims. Claims. One claim. A method for energy production, including feeding a substance in a liquid phase to a treatment zone and creating cavitation bubbles in a substance. Characterized in that cavitation bubbles in a substance are created by creating a periodically changing pressure, having constant and variable components, and these components are selected from the following ratios. P1 from 0.3 to 0.7, P2 plus 0.3 plus P3, P2 plus P3 minus P1 from 1 to 10 sigma, where P1, the constant component of pressure, megapascals, P2, variable pressure component, megapascals, P3, saturated vapor pressure of the processed substance at the temperature of its supply to the treatment zone, megapascals, and sigma, the tensile stress of the processed substance at a temperature of its supply to the treatment zone. At a temperature of its supply to the treatment zone. Boom! Thank you, Kladov, for this stunning piece of work. And I am shocked but not surprised that such brilliance has been sitting there in patent archives for the last 30 years. I don't blame people from not being able to read these patents, even if you were Russian speaking. It doesn't matter which version you looked at it didn't work. You needed to actually work out what was trying to be said and then rebuild it and then check the equations. But I think it's done. I think this solves the biggest challenge facing Bin-Juine Huang in converting a promising technology into a functioning industrial scale device. And because the patent for the actual cavitator itself is also expired, having been granted, not this one, we have a complete system defined pretty closely that achieves the goal at really nearly megawatt levels of excess energy. I mean, it's when you look at this, it's almost unfathomable that you are getting half a megawatt here of excess energy. You know, in fact, it's more than half a megawatt. It's nearly 3/4 of a megawatt of excess energy. That is absolutely mind-boggling. Look at that. 72 kilowatts in, 836 kilowatts out, using water and just 5% aluminium silicate, standard kind of additive. Again, I want to thank Alexander Shishkin, his own work that he released for the first time in terms of the synthesis of both deuterons and the synthesis of 18 oxygen. He only mentioned that for the first time as a result of the publication in Nature Scientific Reports of Bin-Juine Huang et al.'s paper. And so this is I think this is a to not try and use a pun here, this is a real watershed moment. I think probably this is the most important work that I have done, and it's actually Kladov's work, but being able to get it into a form where it can easily be consumed at a time that we desperately need a solution. Right, so well, it's 0.75 of kilograms. I don't know how much equipment. I mean, these are big devices. Yeah, aluminosilicate, isn't that clay? Yeah, kind of. Yeah. No, aluminosilicate, you can go and look it up. It's I think it actually has hydrogen trapped inside it. But you know, yeah, it's a fairly common thing you can get. Hi, Stephen Behalls, great to have you here. Yeah, this is really it's been an honor to be able to find this pattern, and you know, like I say, when I finish this full translation tomorrow, I will do just a basic read through, and if anyone wants to spend some time to try and improve the Russian translation, I will revisit it. I think it's that important to get this out into the public space with the associated patents. But to reiterate, this work in RU 205460-4C1 from work that was conducted in the 1980s, patent from 2nd of July 1993, nearly 30 years ago. Very well defined work, unfortunately not very well put into the public domain. Probably because the people that were doing it just didn't understand all the volume of things that were going out there. But the fact that this has reference to this 1978 awarded patent of fusion in liquid metals. Obviously, much more complicated to make liquid metals, and this configuration is much more complicated, I believe, than his simple rotary style cavitator. That is defined here. Anyway. Okay, I'm going to have a quick look up. Hi, Cosmic Dave. Hi, Martin Hughes. So, James Vickers is asking how many kilograms of equipment are needed to generate, let's say, 0.75 of a megawatt. It's going to be big. But, you know, I saw a thing the size of a shipping container generating half a megawatt of 400 kilowatts of electricity with the thunderstorm generator. I don't expect it's going to be as big as that. I mean, you don't actually have to have the internal combustion engine. You just have an electric motor to drive the process, you know, that's doing the cavitation. You know, I could imagine ways that you could attach this to a water wheel where you actually have a fall of water driving a cavitator shaft that is generating hot water using the water that's coming in from the water that's just fallen, you know, if you know what I mean, which would be a thing of great beauty. So Felix Audate says, can you give details of the device so that we know what not to do? Well, I think if you have deionized water, you're just going to get, if you have the parameters in the sweet spot, you may get up to a COP of around about 4, 5, 6. Okay. You know, that would be great. That's like twice the kind of a heat pump. I mean, if you have an air source heat pump and you're trying to heat a room to 20 degrees and the outside air is below 5, you actually have to start putting energy in. It doesn't work as a heat pump anymore. You need the air like above 5 degrees in a lot of these systems. Whereas this, well, it doesn't matter if it's minus 50 degrees outside. You know, you can have water in the house, and you can use, you know, a bit of line energy or some solar panels or some wind or whatever. And you don't need that much if you've got a COP of 11, right? Of course, there might be an issue where you have to have some consumables, where you have to change the impellers or the cavitation module. In that respect, Bin-Juine Huang's system is much more simple because it has these injectors, which are more trivial to make than these rotating systems, and more robust. Very similar to the Soviet or the Russian Federation cavitation heat generators, which are just producing a COP of around about 1.5. But you know, this is brilliant work. It's just, and so many opportunities. So I had a discussion with a sponsor of the project yesterday, and you know, we would be interested in creating CAD drawings for these things to be CNC'd. So it'd be a case of do the CAD drawing, CNC one up, do the experimentation, verify the parameter space in which it should work, and then, you know, that yeah. These things should be able to be easily mass produced, and the control logic should not be complicated. And of course, you're using water. So James Vickers, the idea of absorbing 70 neutrons per second does not sound so dangerous to me, but does anyone have a more educated opinion? 70 neutrons is what the detector is absorbing. It's not necessarily the amount of absorption that you would get as a human standing next to it. You might be getting a hell of a lot more. Also, you know, since this work was done of Kladov, obviously Shishkin observed the emission of strange radiation, which has its own health risks. So, you know, it's not to say that there isn't a form of radiation that isn't, you know, going to cause a risk, but the actual point about this is, as he described, you would do this in a situation of like community heating. For instance, if you go to Iceland, they use geothermal energy, and the hot water is pumped into the towns and villages, and you could imagine a similar scenario where the device is just, you know, outside or somewhere else. Let's say you're living in off-grid or whatever, and you've got your thermal water generator, and you just park it, you know, a couple of 100 meters away underground or whatever, and the radiations that this could typically produce basically stop almost immediately. The device is shut down. So you know, it would be safe to maintain, and you would have it in a situation that is safe to operate. But certainly, I don't want anyone to be put at risk. But there are, you know, if you go inside a normal nuclear reactor, you're going to have issues. But this is far, 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 far simpler to produce than a normal nuclear reactor. So. Yeah, Lithnik says, like, with this level of efficiency and direct on-demand local generation, you could use this to heat up roads and clear ice. Yeah, I mean, you would have like an under road, you know, like underfloor heating on key routes and stuff. So William Schwant is asking, can you simplify it a bit? Is there a way to use there right now if we tweak it a bit? I think like most of the hard work has been done by Kladov, and then it was put into some patents which were literally unreadable. I've now made it readable. This is the parameters that Bin-Juine Huang was wanting to nail down in order to be able to know how to hit the sweet spot and produce excess heat. It's already been done by Kladov, and therefore we can shortcut that particular challenge. This means that hopefully this will accelerate his work. It will also accelerate acceptance that this can be possible, because he is an active researcher able to produce a lot of reactors in a short space of time and doing the radiation studies. Now, my question is, these devices are big, right? They are in the hundreds of kilowatts range, right? Is Bin-Juine Huang's device sufficiently aggressive enough to actually produce sufficient radiation for it to be detectable? I don't know. I kind of think that the one that's most likely to be able to be detected, because it's 2 orders of magnitude higher, is the neutron radiation. Okay, and because it basically switches off afterwards. I mean, it might. There's a very small chance it might make some of the reactor hot, but I don't know if it's not. If the energy of the neutrons, I don't know if there's no ability for them to be interacting particularly. You know, you would only need to do it enough to show that yes, it's doing a nuclear reaction. But you know, it's all you're doing is you're trying to bring people into the fold who literally their ability to accept something is contingent on very specific things. And the work has already been done by Kladov. The most important thing here is to be able to achieve the effect and stay within the parameter space that allows you to get this lovely range of useful gains in heat. I mean, as soon as you're getting over a gain of 3 times, you're in heat pump area, but you've got a simpler device. It's much simpler. So Cosmic Dave says miniaturization is the key. Well, you know, have you seen the Clater and Stringham ultrasonic transmutation experiments? Well, it was meant to be producing heat, but it produced transmutation. I mean, it's the actual reactor is not much bigger than, I don't know. It's not much bigger than this microscope. It's not much bigger than that microscope from that part upwards, you know. So define how small you mean. I think the limit here is to get the higher levels of excess heat. You know, these 5.65, 4.5, 6.46 levels. You need the parameters to be, you know, quite a high level of pressure, but I think it's eminently doable. So Larman Ball says use of heavy water would produce a much higher COP probably. Shishkin, and like you're going to see this in the next few days, he already synthesized deuterium and oxygen 18. So those are the 2 things that are going to help make water heavy from his cavitator. So this makes it heavy water if you keep cycling it around. You know, it might be that you cycle something around for a number of cycles and then you dump that water, and essentially what you're doing is you don't want to get it to the point where it's starting to produce things that you don't want to produce, if you know what I mean. So Aodonis says, look at the trouble hot fusion goes through for practically no excess heat. Well, yeah. I mean, there was a lot of celebration, I said at the beginning here, of this 60-something megajoules of energy from the jet in the UK. But in 2019, I presented the 2017 data from Dr. Alexander Parkhomov for his 225-day reactor, and that produced 4.2 something gigajoules, which is 60 plus times more than they produced. But their COP was less than 0.2, whereas the COP of the Parkhomov reactor, since it was a heater, never fell below 1. It was a heater that produced up to 1 point something kilowatts excess heat at various points, and I think 220 watts over its entire 225-day range. So, but these kind of devices, if you've got a device that's producing basically a third of a megawatt, I mean, it's absurd, really, isn't it? Cosmic Dave, yes. So here, if you add aluminosilicate, and I showed here that you can take aluminium and silicon, which he chose this additive, and we know that silicon we know that aluminium is formed. Aluminium fuses to iron. We've seen this in various different experiments. Then the use of aluminosilicate in this 5% solution is from 72 kilowatts input, yielding 836 kilowatts output. That's 11.61. That's bordering on 12. William Schwant, I would expect nothing. You have to be within this very specific range in a specific pressure and cycling it. Yeah, so between 11 and 12, depending on which way you're looking at it. Which is, you know, if you look at the average air source heat pump, you're probably looking at about 4 times the, probably 4 to 6 times the average output of an air source heat pump. Okay, William Schwant, you go for it. Okay, so I think I'm going to close this one down. I want to have some time tomorrow to finish the translation of the chart here and to do a read through succinctly to make this a nice self-contained blog. I will add to the blog for this live stream all of the relevant patents that I've discussed today. This allows a nice little addendum to Bin-Juine Huang's paper, and it allows a forward direction in terms of being able to potentially increase the excess heat and settle some of the debate for the naysayers out there that think that cavitation can't do anything, it's just bubbles in a soda bottle. Okay, so thank you very much for your time. This was Method for Obtaining Energy by Anatoly Fedorovich Kladov, someone who I mentioned for the first time in my Ultra presentation in Azizi in September 2022. And it was my reference to Kladov's 1980s cavitation work and this 2 to 7 times excess heat out of just water. And what we learnt today was that there is no noticeable radiation outside of background in the system when it's just run using the parameters with just water in a flow-through mode, but that he realized that he could synthesize elements by running the water round and round and round for a longer period of time, and this probably led him to understand that in cavitation, the processes when the bubble formation, temperature, and material science properties and the actual impact and pressures involved were within a specific band generalized for the properties of materials. You get changing of the structure of a nuclide by adding one or more structural elements, changing the structure of the nuclide by dividing into several fragments, and changing the structure of the nuclide by dividing it into the smallest structural fragments, or by the complete transformation of matter into radiation. And you can also remediate nuclear waste. So it is a huge thank you to Anatoly Fedorovich Kladov, and thanks again to Alexander Shishkin for his passing on to me the paper, the first access to a patent, and that led me to be able to find the other ones and decode the available information out there into a reasonably accurate English resource that people can use for generating replications and working embodiments, and that should hopefully accelerate the work of Bin-Juine Huang and his team there in Taiwan to develop commercial, industrial scale, long-lived, long mean time between failure, heat generation devices based on cavitation. Thank you very much for your time. I will see you in the next video.